Hello, my name is George Seelinger, and I am a fifth-year grad student at the University of Virginia, and I would like to talk about K-theoretic Catalan functions. This work is joint with Joanna Blasiak and Jennifer Morse. So let's dive in. So first, I'd like to talk about Schubert calculus, which provides the setting for and motivation for this work. And then before talking about K-theoretic Catalan functions, I'd like to talk about normal Catalan functions so we can work our way up. So first, Schubert calculus. The general idea of Schubert calculus is that you want to find the number of points in an intersection of certain subvarieties in a variety X. However, this can often be translated into a question in cohomology, where you take the representatives for your subvarieties, and then the cut product structure will give you the structure constants that precisely correspond to the number of points in this intersection. Finally, and sort of key to Schubert calculus, is that you can often find a special basis of polynomials such that their structure constants actually are the same as the ones in the cohomology, and thus also encoding the number of points in the intersection of the subvarieties. So from my perspective, working in combinatorics, what I like to do is study these corresponding polynomials and try to understand new properties about them that then enlighten the geometry and cohomology theories that they come from. So in particular, I want to identify them in explicit and simple terms that allow us to compute things and prove new theorems. So let's look at the most classical problem for Schubert calculus. So this setting here is the Grassmannian, and here there are these well-known Schubert varieties that are indexed by partitions lying inside a rectangle. And we're interested in finding the number of points in the intersection of these Schubert varieties. In this case, there's the Schubert basis, which are the cohomology classes representing these Schubert varieties, and the cut product structure does indeed correspond to the number of points in these intersections. Finally, it was discovered that there's a special basis of polynomials called Schur polynomials that, when they multiply together, also have structure constants that encode the same information. However, these coefficients are actually combinatorially understood pretty well. They're called Littlewood-Richardson coefficients, and they arise in other areas of mathematics too. So therefore, by understanding these Littlewood-Richardson coefficients and the Schur polynomials, you're able to then gain information and understanding about the geometry of the Grassmannian. So let's talk about these Schur polynomials a little bit more, because they'll play a pretty big role in our final results too. So first, to talk about Schur functions, let's talk about complete homogeneous symmetric functions. So these are polynomials in an infinite number of variables, and we can associate to each integer a polynomial, but of course if the integer is negative, we'll set it equal to 0. And otherwise, if an integer is 0, it'll be 1, and then otherwise we have this formula. Furthermore, if you have symmetric functions, you can multiply them together and get another one, so we can actually, for each integer vector, we can associate a symmetric function by just multiplying these h functions together. Then we can act on them with this tool called a raising operator. So a raising operator will, if you think about the h's as indexed by these integer vectors, simply subtract 1 from the jth coordinate and add 1 to the ith coordinate. Often people like to represent in combinatorics these integer vectors as Ferr's diagrams, where you put a number of boxes in each row to represent the number in the vector. So this is how then the raising operators get their name pictorially, because they take a box from, say, row 3 here and move it up to row 1. If similarly, in this other example, we act on this shape and bring up a box from row 3 to row 2. So notably, we're working here with integer vectors, and so the result may or may not be an integer partition. But this makes total sense with the definitions we have from above. And then finally, now we can define, using these raising operators, a Schur function. So a Schur function, this may not be a definition that is as common as others, but it is true that it can be defined using the raising operators in this way. And this is sort of equivalent to what's sometimes called the Jacobi-Trudi identity, which is a determinant of a matrix. So it's sort of an exercise to show that you can actually rewrite that as this raising operator identity. So there are many variations of Schubert calculus. So the one I just presented is very classical for like a standard type A Grassmannian, but here are a bunch of other examples of cohomology theories and that have Schubert calculus associated with them in some sort of polynomial representative. I'm not going to talk about all of them, but I want to focus on the last one here. So I want to focus on the K-theory and the K-homology of the affine Grassmannian. This theory actually simultaneously generalizes the K-theory of the Grassmannian and also the cohomology theory of the affine Grassmannian. So we're going to need to talk a little bit about each of those since they'll inspire and be generalized by our work in the K-homology of the affine Grassmannian. So let's talk about what's known in each of these situations. So the first is that the K-theory classes of Grassmannians, just the normal ones, not affine, are represented by a class of polynomials called Grothendieck polynomials. Since we're going to work in a homology setting, we're actually going to be interested in their dual. So that's represented by this little g, and it's defined very similarly to Schur functions. You take this raising operator expression and you act on, instead of an h function, a function I'm going to call k, which is just some inhomogeneous analog of the h, which is necessary for the K-theoretic situation. The homology classes of the affine Grassmannian are represented by something called K-Schur functions when they're specialized to t equals 1. And we'll get into those in a second when we get to Catalan functions. But importantly, Lamb, Schilling, and Shimizono studied the K-homology classes, the affine Grassmannian, which are called K-k-Schur functions, but they did not provide a direct formulation. Rather, they just defined them as some dual basis to another basis in the K-theory, and this left a lot of open conjectures because it's hard to work with such a definition. It's very inexplicit, and so you can't really easily compute a lot, and it makes it even harder to prove things about specific K-k-Schur functions. But remember, my goal, and the goal of Schubert calculus generally, or one of them, is to identify these representatives in terms that are actually useful to compute and prove things. So in this sense, I would like to propose a new definition that we'll work our way to using K-theoretic Catalan functions. So to work with Catalan functions, generally we need a notion of something called a root ideal. So a root ideal of positive roots is equivalent to a Dick path, which is just some lattice path above diagonal. So I've depicted here in green, here's a diagonal line, and then in green is a lattice path that lies above that diagonal. And this separates the squares lying above the diagonal into roots and non-roots. So the roots are colored here in red, and the non-roots are colored here in blue. And so any one of these paths form the root ideal, which is technically the roots, the ones that are red. However, we'll also be working with the blue non-roots. So then a Catalan function is given such a root ideal and an integer vector. You can form a raising operator expression from the non-roots only, so the blue ones here, that act on a homogeneous symmetric function. Let's so look at some limiting cases here, and if we of course take the red part to be empty, so we take all the blue roots, we then recover our Jacobi-Trudi identity from before, thus giving a Schur function. And if we take our root ideal to be all the roots, then of course they're all red, there are no blue roots, so this blue set is empty, the non-roots are empty, and therefore you're just left with the complete homogeneous symmetric function, and there's no raising operator expression acting on it. So in this way, you can sort of think about Catalan functions as interpolating between Schur functions and complete homogeneous symmetric functions. All right, so now let's look at one of these sort of interpolation families. So a K-Schur root ideal is one where you fix an integer k, or non-negative integer, and then you take some integer vector, and associated with it you can create a root ideal, and maybe this is best illustrated by example. So here we take k is equal to 4, and then we'll take the this integer vector, so 3, 3, 2, 2, 1, 1, and then we write it along the diagonal here, just as sort of a trick to make it easy to draw the picture, and we need to add in each row a number of non-roots such that the index here of the vector plus the number of non-roots is equal to k, which in this case is 4. So in the first two rows you can see you have a 3, and then you add plus 1 non-root to get to a total of 4. Here on the third row and fourth row you have a 2, and then you add 2 non-roots in order to get to a total of 4 total. And eventually you run out of space, but if this continued, a 1 would eventually have 3 non-roots, and so on. So then, using this K-Schur root ideal, we can provide a explicit definition for a K-Schur function as a Catalan function. So just for any partition, you just take this Catalan function given by this special K-Schur root ideal, and then with the same indexing data. So why would you do this? Well, there were many different definitions of K-Schur functions, but by realizing K-Schur functions in the framework of Catalan functions, Blasiak, Morse, Poon, and Summers were able to prove some facts about K-Schur functions that will then be useful for us in a very straightforward way. So the first is that the K-Schur functions have something that we're calling shift invariance. This looks very technical. It is a little technical, but it's a key link in order to prove that the k plus 1 Schur expansion of a K-Schur function has positive coefficients. This is something that was already known in the t equals 1 case, but they prove this for with K-Schur functions with a general t, and also their proof is much shorter and it's more straightforward than the previously known proof. And then this also implies that the Schur expansion of a K-Schur function has positive coefficients. So in general, this paper was with Catalan functions. There's a deformation parameter t, but we have to specialize t equals 1 for Schubert calculus, and this provides sort of a roadmap for our similar approach for the K-theoretic K-Schur functions. So in order to do this, we're going to need to introduce an extra ingredient, but let's sort of look at why. So remember that the K-homology of the affine Grassmannian simultaneously generalizes the K-theory of the Grassmannian. So here I've just rewritten this formula we saw earlier. So in particular, we're acting on this K here with the raising operator. And then it also generalizes the homology of the affine Grassmannian, which I've now introduced in terms of raising operators. So you have this K-Schur function, and then you have some varied root ideal based on your data, and it's acting on an H. So we somehow need to combine these elements, working with a K and varying the root ideal. But it turns out to do this, we're going to need an extra ingredient. So this extra ingredient is called a lowering operator, but it's pretty simple. It's actually easier than raising operators. It simply subtracts 1 from the jth coordinate of your integer vector. Or if you like looking at the diagrams, it simply deletes one box. So this is sort of what we need in order to glue everything together. So now let's talk about a K-theoretic Catalan function. So we're going to need 2 root ideals, not just 1, and an index gamma. And then it turns out we'll have one of these root ideals giving out the raising operators, which is here, and another one giving the lowering operators, and then you have the index all for the k, and so all of these act on the k. which is once again just some sort of inhomogeneous analog to the h's. And so they might look like this as just an example. You have, as before, our blue non-roots giving out some sort of raising operator expression. And then I'm going to mark the lowering ideal roots with dots here, which then contribute. You just look at their column entry, and those contribute some lowering operators. So then now with this general tool of a K-theoretic Catalan function, we're able to provide an answer to a direct formulation for the K-theoretic K-Schur functions. So for the K-homology of the affine Grassmannian, we take the K-theoretic Catalan function with the raising ideal given by a K-Schur function and the lowering ideal given by a K+1 Schur function, and we show that this has the correct structure constants. So just an example of what these look like. As before, you have your K-Schur root ideal here in blue, and then because you have a K+1 Schur root ideal for the lowering operators, everything sort of gets shifted to the right one. So the general pattern here would be some number of blue roots and then sort of the space, and then you start having the dots for the lowering ideal. So then from this explicit definition, we're actually able to prove some useful properties. So first, as before with the K-Schur functions, we establish shift invariance, which is sort of just this technical thing that then allows us to prove that the branching coefficients are alternating by degree, which in this case is the appropriate notion of positivity for the K-theory. So this was conjectured in Lamb, Schilling, Shimizuno 10 years ago, and with our direct formulation, we were able to actually prove this property. So in the future, now that we have fit the K-k-Schur functions into a K-theoretic Catalan function setting, we believe that this presents opportunities to revisit other questions in this area that haven't been addressed. So the first one is that you have this dual basis of affine Grothendieck polynomials, and we'd like to describe some subset of their structure constants combinatorially. So at the moment, there is no general combinatorial description of these structure constants, but we believe the K-theoretic Catalan framework gives us a way to get a handle on this. We'd like to, while we establish that the branching coefficients are alternating, we'd like to actually combinatorially describe them. And then finally, K-theoretic K-Schur function can be expanded into normal K-Schur functions, and we'd like to be able to, now that we have this raising operator and lowering operator formula for both the K-theoretic K-Schur functions and just normal K-Schur functions, we'd like to be able to manipulate it to perhaps give some sort of combinatoric to describe these coefficients. So thank you for listening, and I hope you enjoyed my talk.